Welcome to Maths with EJD. We're still on partial differential equations, and in this video, our focus will be on Green's functions and the partial differential equations. Okay, to start off, we need to know that in the context of partial differential equations, Green's functions, I think we've made mention of Green functions in passing when we talked about fundamental solutions or so. So in the context of PDEs, Green's functions play a critical role, a critical role in solving linear homogeneous PDEs. These functions are used to express the solution of a differential equation with a given source term, with a given source term rather, in terms of the solution to the corresponding homogeneous equation. Okay, essentially, a Green's function acts as a fundamental solution. Yeah, I think that was where we mentioned it for the first time. It acts as a fundamental solution to the PDE, helping to solve boundary value problems when a system is present. So let's look at the definition of Green's function. Definition of Green's function. So a Green's function g of x, comma x prime for a linear operator, whatever the operator is, for a linear operator L, is defined as the solution to the equation L of g of x, comma x prime, which is equal to delta of x minus x prime. Okay, where delta of x minus x prime is the Dirac delta function. We've seen something about this before. I think when we're talking about Laplace equations, Laplace transforms, is the Dirac delta function, which can be viewed as a point source, at x prime. And as the equation is right, if this were to be 0, then that expression would be homogeneous. But because we have the Dirac delta function, so it's more like a forcing term, and that is why it's a source term in that situation. So at x prime, so here g of x, comma x prime is a function that depends on both the source point x prime and the field point x, and it represents the response at x due to a unit impulse at x prime. Okay, and then we move on to general solution. So general solution using Green's function. Okay, so once the Green's function for a given PDE is known, the solution u of x to the inhomogeneous PDE given as Lu of x Lu of x equals f of x. The solution to that can be expressed as a convolution of the Green's function and the source term f of x, which is u of x equals integral along the domain D gx comma x prime f of x prime dx prime, where D is the domain over which the PDE is defined. This equation allows the solution u of x to be computed by integrating the product of the Green's function and the source term over the domain. Okay, so we get to that point where we switch things over. This comes here, and then okay, let me use that with black. So now let's see examples. Say example 1 now. So for example 1, let's look at Green's function for the Poisson equation. Green's function for the Poisson equation. So I think Poisson equation is more or less like the homogeneous version of Laplace equation, so to speak. So consider Consider the Poisson equation in one dimension, which is the squared u of x dx squared equals f of x for x belonging to 0L with boundary conditions u of 0 equals u of L equals 0. So that simply means that whatever the status at the beginning and the end are the same, they are 0. Okay, so the question is, okay, let's move now. We aim to find the Green's function for this problem. The Green's function satisfies d squared g x comma x prime, it being a second derivative thing, right? Dx squared now equals the Dirac d of x minus x prime. So that's what that satisfies. And then for simplicity, we first solve this equation in two regions. X less than x prime and x greater than x prime. The solution in these regions is a linear function since the second derivative of a linear function is 0. So we have the solution to be g of x comma x prime equals ax plus b for x less than x prime, and it's cx plus d for x greater than x prime. These are the two regions into which we've divided all that. So to match the boundary conditions, g of 0 x prime equals 0 and g of L x prime equals 0 also, which corresponds with the boundary conditions we have. So we solve for the constants. We solve for the constants A, B, C, D. Additionally, at x equals x prime, we need to ensure that the solution has a jump in the first derivative. So that we have dg dx evaluated at x equals x prime of epsilon minus dg dx evaluated at x equals x prime minus epsilon is simply equal to 1. Okay. So this condition now this condition comes from the delta functions, property. So solving these conditions, solving these conditions gives the Green's function for this boundary value problem. So we take example 2, which will mean switching to this, and then let's have this. Example 2. So Green's function for the heat equation. So now consider the heat equation. Partial u of x comma t, partial t equals alpha partial squared u of x comma t, partial x squared, with initial condition u of x comma 0 equals f of x, and boundary conditions u of 0t equals u of lt equals 0. So to find Green's function, to find the Green's function, g of x, x prime t, because we have this 3 now, so we solve the equation. Partial g x, x prime t, partial t equals alpha partial squared g x, x prime t, partial x squared, subject to the initial condition, g of x, x prime 0 equals delta x minus x prime, and the boundary conditions, g of 0 x prime t equals g of l x prime t equals 0. Okay, that's like the transformation into the Green's thing. And if we do all this, the solution is g of x, x prime t equals summation from n equals 1 to infinity sine n pi x over L, then sine n pi x prime over L, then e raised to power minus alpha n pi over L all squared. Okay, so that's what we have in that case. Of course, I mean, I've skipped several steps, But if you're interested, you may want to investigate this further. Okay, but it pretty much looks like the kind of results we got, using other methods. Okay, so this Green's function, this Green's, this Green's function expresses the solution to the heat equation as a sum over modes with each mode decaying exponentially over time. And that's why heat equation, for in the heat equation, you have in the beginning, the heat is highest, and then it keeps reducing towards the end. Okay, so in summary now, Green's functions provide a powerful way to solve linear PDEs with arbitrary source terms, like we've said. By finding the Green's function for a given problem, one can use it to construct the solution by integrating over the source term. The process involves solving the PDE with a delta function source, incorporating boundary conditions, and applying the concept of superposition to obtain the general solution, pretty much like some of the things we've said previously. So these methods are applicable in a variety of contexts, including electrostatics, heat conduction, wave propagation, and fluid dynamics. So the Green's function approach is particularly useful in solving problems with complicated boundary conditions or geometries where direct solution methods may be impractical. To visualize what we have done, let's look at the Python code for this. So here it is, you have the Green's function and PDs. So here we have the length of the domain. Let's call that one, which can vary. Number of grid points, call it 100 if you like. Then in this case now we have the source term f of x. So we define it as a specific expression, which is a simple Gaussian function minus 100. This is e raised to power minus 100 x minus 0.5 raised to power 2. That is what we take here as our source term f of x. So then we define the Green's function for 1D Poisson equation with Dirichlet boundary conditions. So we have all of that going on here. And then we define a function called solve Poisson, and we create a grid of points in the domain where x values is 0 to L divided into n equal steps. Then we initialize the solution array to be u value equals this, and then numerically compute the solution using the Green's function. So for ix enumerate the x for each x value now. So you get the integral value, and you have quad lamb x prime, blah blah. So by the time you go through this, you have a good grasp. So I just click on this and run it, and then we get this expression. So that's the solution to the Poisson equation using Green's function. So you see the source term f of x is this red one. So that's more like, it's like when the process starts, that's the heat you're supplying to the system. And the actual solution at the end of the day is this blue line. Okay. So pretty much like what happens, like you have highest heat when it starts, and then it decreases to the final solution at the end of the day. So that's the idea of the Green's function. Okay. So I think I have one or two questions we can play with here. Okay, we've done the Poisson equation. Guess we can do a wave one. Yeah, so practice. Consider the one-dimensional wave equation. That's question one now. That's partial squared u x comma t partial t squared equals c squared partial squared u x comma t partial x squared for 0 less than or equal to x less than or equal to L and t is greater than 0 with initial conditions u of x comma 0 equals 0, and then partial u of x comma 0 partial t equals f of x, like the point source or so, and boundary conditions, u of 0 comma t equals u of l, u of 0 comma t equals u of l comma t equals 0. So A, find the Green's function and the Green's function for the wave equation. Obviously, the operator L we saw initially is actually the second derivative in this case, because this is second derivative, and on the other hand, it's also second derivative. So you now have B to be, in B, use the Green's function, to compute the solution u of x comma t given the initial velocity f of x. Then number 2, solve the Laplace equation in 2D using Green's function, and that equation is nabla squared u x comma y equals 0 for x, y on the two-dimensional real number system. Then we can consider a circular domain of radius r with boundary condition u r comma theta equals g of theta, where g of theta is a given function of the angle theta. So again, in this case, you are expected to derive the Green's function for this problem and use the Green's function to find the solution u of xy inside the disk. Okay, let me write that too. Okay, derive the Green's function for this problem, and B, use the Green's function to find the solution u of x comma y inside the disk. Okay, so let me see your answer in the comment section, either on Facebook or on YouTube. And be sure to let me know if there's a problem you'd like to solve or a topic you'd like to teach and how helpful these videos are for you. Please feel free to let me know. Be sure to also subscribe if you have not done that already. And if you have, please be sure to also hit the notification bell so you can always get alert each time a new video is released. Don't forget to like and share also so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.